Hey friends, welcome to Rational Exponents Day 1. I'm going to try to streamline these notes today just so the video isn't super long. So I'm going to skip the warm-up. We'll do it a different day. And I actually want to start down here with what rational exponents mean and kind of connect them with some things that we might already know. So like we discussed, rational means that you can express the number as a ratio of two integers. Really, you can write it as a fraction, right? So when we have a rational exponent, that just means that our exponent is a fraction. Now, one of the cool things is when we have rational exponents, we can rewrite it instead of a power as a root. And so we see this conversion that if you have a number raised to a fractional or rational exponent, we can convert it from a power to a radical, where this bottom term, the denominator, comes out and becomes our index of our radical. You'll see that the exponent, the numerator, still stays the exponent, the numerator of the power. It's that denominator that comes out and becomes the index of our radical. Now, I think the most common one that you may have seen before is if you have x to the 1/2 power, this is equal to the square root of x to the first. So we see that denominator become the index of our radical. So this is very common. X to the 1/2 is the same as taking the square root. So similarly, x to the 1/3 is the same as taking the cubed root. X to the 1/4 is the same as taking the 4th root. Now it's going to get a little bit more involved, but I want to pause here because where we see these powers where we're taking the square root, the cubed root, and the 4th root, what we're going to be seeing are those powers. So I want to just refresh our memories, if you don't know them already, of listing some of these out. So we know perfect squares. I know I've had you guys write them out before. So perfect squares, these are numbers that are raised to the second power, right? So our perfect squares, 1 squared is 1, 2 squared is 4. Go ahead and write these out all on your own. You should know these already. I believe we did this already in class. 64, that's 8 squared, 9 squared. Okay, and I assume you guys know all of your perfect squares. But what I want to look at now are the perfect cubed numbers, not our triples, but our cubed numbers. So these are numbers that are raised to the 3rd power. Now, we're not going to memorize that many, but just a couple of the common ones. So 1 cubed is 1, 2 cubed is 2 times 2 times 2, which is 8. 3 cubed is 3 times 3 times 3, 27. 4 cubed, 4 times 4 times 4, 64. 5 cubed is 125. These are really common perfect cube numbers that you might see. And then we have powers raised to the 4th. 1 is just 1. 2 to the 4th would be 8 times 2 is 16. 3 to the 4th is 81. Those are some of the common ones there. And then if you even want to get some extra credit to the 5th power, 1 and 32 are the common numbers that are raised to the 5th power. So these are just some numbers. The more familiar you are when you see them, it'll be easier when we go to reduce them with our rational exponents or with our radicals, okay? So keep that in the back of your mind. You might even want to, drag this down with us as we do our work. It might be easy to reference if it's down here. Okay, so we see kind of like what I just said, the a to the 1 over n is equal to the nth index of a. And just like we saw here, x to the 1/3 is the cubed root of x. So let's see how we can use this transformation from a rational exponent to a radical, the knowledge of these numbers to help us reduce some of these powers with rational exponents. So we'll start off easy. 9 to the 1/2. We can convert this to a radical where the bottom comes out, right? So the 2 becomes the index, and then 9 just stays inside. 9 to the first power. The square root of 9 is 3, right? So that's something we can do in our head because we know our perfect squares. So if we look at this one then, if we convert this, take the bottom out, right? The denominator of the rational exponent becomes the index of our root. We have the square root of negative 169. So this is the conversion. We're going to talk later about some intricacies with this one, just little foreshadowing here. But here we have the conversion from rational exponents to radicals. We'll keep going. Here, notice we're going to have 8 to the first underneath, but that bottom out brings the 3 to our index. So this is the cubed root of 8. So this is asking what number times itself 3 times equals 8. Now, if you know your perfect cube numbers, we know that the cubed root of 8 is 2. So this equals 2. Right? So knowing these numbers that we listed above is going to be really helpful. If we keep going, if we have 16 to the 1/4, the bottom comes out, right? Your denominator comes out, becomes your index. So it's the 4th root of 16, the 4th root of 16. So what number times itself 4 times equals 16? Well, if we know our perfect, our numbers are perfect raised to the 4th, that is again 2, right? So this equals 2 as well. Awesome. And then this one we have to be careful. There are no parentheses including that negative. So this is like saying -1 times 64 to the 1/3. So if we follow that, we're just going to keep multiplying. That bottom comes out. So this is the cubed root of 64. So what times itself 3 times is 64? Well, 4 times 4 times 4 is 64, right? That's one of our perfect cubes. So this equals -1 times 4, which is -4. Okay? So what I'd like you guys to do is using these perfect squares, these perfect cubes, all these numbers that we should be memorizing, I'd like you and your group to try the next row. So you're going to pause the video and try, you're going to try not the whole next row. I'd like you actually just to try this one. See if you can use your powers and your knowledge of exponents to try this one. Okay, so you're going to pause the video and try this one here. All right, so hopefully you were able to come back and distribute that 1/3 exponent just like we would any other exponent. But when you distribute it, that 1/3, remember, is the radical. It's the converts that radical, and then we can continue simplifying from here. So the cubed root of 64 is 4, cubed root of 125 is 5, and that is our answer. So not only are we converting from exponential power to our radicals, but we're also using our properties of exponents along the way. So what about these guys where it's not just 1 over, right? The exponent isn't just 1 over a number. We have a cubed or a squared. What do we do with these? Well, let me show you. So if we follow the bottom out idea, the denominator comes out and becomes the index. The 8 goes underneath, but that numerator now is going to follow the 8. So this is the cubed root of 8 squared. The cubed root of 8 squared. So here we have some options. We can simplify what's inside. So 8 squared is 64. And then from there, the cubed root of 64 is 4. Knowing your perfect cubes and those numbers we reviewed before makes it a lot easier. 25 raised to the -1/2. So this is 1 over our number, but this time what makes it interesting is this negative. Well, we know our properties of exponents tell us that that means the 25 is not happy in the numerator. It wants to go to the denominator. So we're going to cross the line, change the sign of the exponent, And then from there, we can convert to a radical. So this is the square root, bottom out, right? The square root of 25, we get 1/5. All right, and we'll do, this one will be the last one as far as evaluating or simplifying. So here, bottom out, it's going to be the square root of 49, and then that numerator is going to follow the 49 here. So this is where it could get a little bit tricky. We can rewrite it like this, which would be fine. Or we can also think of it as, instead of keeping that cubed with the 49 under the radical, we can also rewrite it like this, the square root of 49, but now cube the whole thing. So we have this option where we can put the numerator inside with the base, or we can cube the whole thing. So in this particular problem, since 49 is a perfect square, it would make sense to simplify and do it this way with the exponent outside. This one is easier. So square root of 49 is 7, and then we're going to cube 7. Now we didn't cube 7 before. This equals 343. This is one of the lesser known cube numbers, but it's a perfect cube nonetheless. All right, I hope that makes sense. Put a star or mark any that you want to go over in class tomorrow, and we'll do that. So being able to simplify with our rational exponents by converting to radical is important. We should also be able to apply our properties of exponents like we did earlier in our lessons. Follow those exact same properties, but just do it when our exponents are fractions. So for example, to refresh your memory, if we had x to the fourth times x to the first, we would get our answer by adding the exponents. So it would be x to the fifth, right? Now that's the same if our base is x, or if our base is, let's say, 6. If we had 6 to the fourth times 6 to the first, we could say our answer would be 6 to the fifth, right? Again, if we add those exponents, we get our new exponent. So if we follow that same property, look at this first example here. We have the same bases, and we're multiplying the property, or the powers. So what we're going to do is add the exponents. This is going to equal the same base raised to the sum of the exponents. So that when you add fractions, the denominator stays the same. You add the numerator. So we have 6 to the 5/3 power. Now, we aren't able to simplify this at all. If we wanted to convert to radical, it'd be the cubed root of 6 to the 5th. We don't need to simplify as far as this goes. I'm okay right now with us just practicing the powers of exponents with the rational exponents. So we're okay just stopping here. So let's practice another one. So same sort of thing. The base stays the same. Because we're multiplying the powers, we can add the exponents. So the denominator stays the same. We add across the numerators. This, our rational exponent, ends up simplifying. 6 divided by 3 is 2. So this one we actually can evaluate all the way and get 9. All right, following right along, continuing. So this is going to, base will stay the same. We add the exponents, so the denominator is 5. -4, oops. It has a -4 plus 2 is -2. So what I would say here is simplify so that we have positive exponents. So this guy wants to cross the line, change the sign into the denominator. So just 1 over 2 to the 2/5 power. Okay, so all three of these use this property of when you multiply the powers, you add the exponents, right? So one of the other properties we talked about was what happens if you're dividing the powers. So if you had x to the 7th divided by x to the 9th, what would you do? Well, we talked about that we would subtract the exponents. And if you get a negative, that means the exponent would want to be in the denominator. The power would want to be in the denominator because it's negative. it wants to cross the line and change the sign, right? So we subtract the exponents when the powers are dividing. So the same thing's going to happen here. We're going to take those powers, 4/3, and now subtract 2/3. When you subtract the 2, you get a positive 2/3, which means our answer will be in the numerator. It'll be 2 to the 2/3 power. Again, I'm not going to make you go that extra step to simplify if you can. We're just applying the properties at this point. All right, 2 more examples, then you can start your homework. So here, just mixing a couple properties together. So first, we have a power of a power, so we want to do those first. And remember, when you have a power of a power, you multiply. So for us, the numerator would be p to the 3/4 power of a power, you multiply. And the denominator, when we multiply here, think of this as 2/1. So 5 times 2 is 10. 4 times 1 is 4. So that's going to reduce to 5/2. So we did the power of a power. And now we need to subtract. Well, when I look here, I'm going to subtract these fractions. I see I don't have common denominators, but there's that 4th I want. So I'm actually going to keep it just for my convenience. I'm going to keep it as 10/4 right now, unsimplified, because it's going to just make the subtraction easier. So 3/4 minus 10/4 is -7/4. So that negative tells me that my variable, my power, should be in the denominator. When I move it to the denominator, the exponent becomes positive, and I just put a 1 in the numerator. All right, awesome. And last but not least, we have kind of put them all together here. So sort of following our order of operations, we want to do what's inside the parentheses first, right? So since we're multiplying the powers, we're going to add the exponent. So inside the parentheses, I'm going to keep that the same, that the same. Just looking inside, when I add the exponents, -1/5 plus 3/10. In order to add the fractions, they need common denominators. So I'm going to multiply this fraction by 2 on top and bottom to get a common denominator. So this is equivalent to -2/10. So -2/10 plus 3/10 is +1/10. So this is y to the 1/10. Okay. So now that I simplified what's inside, now I can do the power raised to another power where we multiply. So 20 times 1/10, 20 divided by 10 is 2. So I have y squared divided by y squared. Anything divided by itself is 1. I love when problems come out to like something that starts off super complicated, looks super messy. Just by applying a couple rules, we get something nice and neat. Awesome. All right, guys, that's where I'm going to leave you. If you need to rewind and go back or check in with your partner if you missed something, please feel free to do this. You can always watch the video on your own again and rewind whatever part you missed. But now you should go to worksheet 1 in your new worksheet. Where am I? Here we are. So we have worksheet, I'm sorry, not worksheet 1. You guys are doing, oh my gosh, I'm all mixed up here. You guys are doing Delta Math, that assignment number 1. So go ahead and jump on, and I'll see you tomorrow.